Hypothalamus Artificial Intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference, Artificial Brains, a new vision of the artificial intelligence for Industry 4.0. The index contains the topics considered at the conference. Conference prepared and edited by Jesus Velasquez Bermudez. His resume may be found on LinkedIn. Engineer Jesus Velasquez Bermudez wants to make it clear that his knowledge in neuroscience is very limited, and that therefore inaccuracies can be found in some concepts of this presentations. Its knowledge comes from the serious study of many scientific works of experts in the field, which have helped to visualize what is presented here. On the other hand, it is also made clear that Engineer Velasquez Bermudez is not an advanced expert in traditional artificial neural networks. He understands them properly. The vision that prevails is that of a mathematical modeler, with extensive knowledge of the appropriate mathematics to perform this work. Human intelligence has two ways of making decisions. The natural one that began to develop with the first human beings. This intelligence is based on the mental model of the individual, which relies on beliefs, intuitions, empiricism, but is generally weak in its intelligent support. We could define it as the intelligence of good practices. Today fully extended by the ochlocracy generated by social networks, which imposes truths without real support. Unfortunately, it is the most used by humanity, and the scientific, based on the knowledge developed by the human being, supported in mathematics as the way to explain the real world, which generates a structure of thought totally ordered, better known as the scientific method. Unfortunately, it is the least used by humans. Evolution of intelligence, from Homo habilis to artificial intelligence. The first evolution of the human being starts from the gibbon, which begins a large physical evolution that will end up being what we know today as a human being. Australopithecus begins a detailed physical evolution that will end up being what we know today Homo sapiens. In this process, scientists have located different types of humans differentiated by their physical appearance and intelligence. Our greatest interest is the evolution of intelligence, which is far more impactful than our physical evolution. The first important step should have been the migration of Homo habilis to Homo sapiens, which would be characterized by the emergence and formalization of language, which helped an evolution in pattern recognition, from the physical to the psychological. Homo sapiens should have migrated to today's standard man, supported by an intelligence based on pattern recognition. From today's standard man, the development of intelligence is mainly oriented to the development of mathematics, which generates in humanity the ability to discover knowledge, and to create new knowledge. The first big step was the creation of algebra. It should be noted that we have not said that mathematics is the only source of intelligence growth. From the formalization of algebra, to the way of expressing the real world mathematically, human intelligence evolves, until it reaches an intelligence based on mathematical and creative thinking, of which it could be said that its current representative is Albert Einstein. Unfortunately, it must be recognized that not all humans reach Einstein's level of intelligence, and that currently the intelligence levels of humans are distributed from Homo habilis to Homo mathematic. Since the creation of the digital computer, the development of artificial intelligence has been the dream of scientists. To date, this dream is being realized, focused on imitating and overcoming the pattern of recognition of the current standard man. The research developed by HI focuses on developing artificial intelligence, supported by the mathematical management to which humanity has arrived, to express physical, economic and social processes, following the functioning of the human brain. There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In 1972. In the book Human Problem Solving wrote by Alan Newell and Herbert Simon. Mathematical Revolutions, From Arithmetic to Parallel Thinking, A Brief History of Mathematics, focusing on the evolution of optimization applied to real-world problems. Muhammad ibn Musa al-Khwarizmi, mathematician and Arab astronomer, introduced European mathematicians into the Indo-Arabic numerals and in the fundamental principles of algebra. Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world. In 1983, Tony Van Roy created the cross-decomposition approach to solving large-scale optimization problems, based on partitioning and decomposition techniques, and mixing different types of methodologies, such as Lagrangian relaxation and Bender's theory. The union of large-scale technologies with parallel computing is increasing every day. The image indicates that a complex optimization problem, which can be solved in a unit of time, say an hour, using simple sequential methodologies, could take 400 hours, 16.66 days. If the appropriate technologies are not available, an unsuspecting professional would conclude that the problem cannot be solved in a reasonable time. Human intelligence, language, pattern recognition, decision-making and creative thinking. Language is related to many cognitive functions such as attention, orientation, communication, and memory. Language skills are not located in a specific brain area but in many of them. Traditionally, Broca's area, located in the left frontal lobe, and Wernicke's area, in the left parietal lobe, had been attributed to the production and processing of language, but today scientists know that many more regions are involved. We must abandon the idea that there is a brain area that is responsible of this. Broca's area was discovered in 1861 by French surgeon Paul Broca, who found that it serves a vital role in the generation of articulate speech. Our ability to articulate ideas, as well as use words accurately in spoken and written language, has been attributed to this crucial area. Wernicke's area serves for language comprehension, and the exchange of information between these areas, as in reading aloud, is done through the arcuate fasciculus. Human knowledge is supported by two types of models. Mental model: it is the abstraction or conception of what is perceived by individuals about a given issue or problem. Mental models are constructed with the knowledge, experiences, assumptions, perceptions, intuitions, informal inductions, deductions, and values of the individual. They are elementary models that are not exposed in public and therefore have a validity limited to the individual. They have their origin in the evolution of the human being, hominization, from the most primitive ancestors, Australopithecus, to the appearance of our species as we know it today, Homo sapiens. All human beings manage mental models, very quick to solve, and, in their absence, easily copy themselves from a more influential individual, and more recently, are implanted in human beings through the ochlocracy of mental models distributed by social networks. When intelligence works under this model, we will call it mental intelligence, which exists and develops in all humans. Mental intelligence and pattern recognition. Mental model is oriented to identify patterns, its foundations are not mathematical, and respond to data processing, and evaluation of eventual, and systematic, experiences. It is based on good practices. Pattern recognition is a data analysis method that uses machine artificial intelligence algorithms to automatically recognize patterns and regularities in data. This data can be anything from text and images to sounds, or other definable qualities. Pattern recognition systems can recognize familiar patterns quickly and accurately. Pattern recognition is the activity that most performs the human being, for example identifies images of people, foods, hydroclimatic conditions, traffic conditions, texts, sounds, and etc. All this with the aim of establishing the conditions of the environment, in the past, the present, and the future, and based on this knowledge make decisions. How the brain identifies patterns is not properly known, but it is mimicked by traditional artificial intelligence. Second, mathematical model is a scientific representation which make use of mathematical language to describe or to explain the portion of reality that is of particular interest to an individual. It is the result of the research carried out by certain humans. The mathematical models are growing as analytical tools that provide greater processing speed to the investigation. For its understanding requires formal training in mathematics and in the science being modeled. These models increase the intelligence of human beings, creating large differences, chasms, between them. When intelligence works under this model, we will call it mathematical intelligence. This ability to understand mathematics, and to handle it, does not extend to all humans. It is necessary to acquire knowledge and experience to handle this intelligence properly. At present, its development is directly related to the ability to handle computational and mathematical technologies. Mathematical intelligence and decision-making. Decision-making process is the final objective of any person or organization, which seeks to make the best decisions from its point of view, its criterion. This process, when carried out in real time, requires a great capacity for mathematical calculation, to handle the complexity of the real world, which increases over time, since the universe increases its entropy at each moment. When humanity began its evolution, it only had mental models to support its decisions, which seriously limited the speed of the evolution of the species, due to the little, almost zero, capacity of mental models, which led the human being to make decisions with very few calculations, or without them. Thanks to analytical intelligence, human beings developed their mathematical intelligence, which has led us to Industry 4.0. To evolve from mental intelligence to mathematical intelligence, the human being requires another type of intelligence that allows him to perform the analyses to understand and discover the models that govern the universe that is written in the language of mathematics, Galileo Galilei. We will call this intelligence analytical creative intelligence. This intelligence can be considered as the highest level of human intelligence, since it is what allows to grow in the discovery of mathematical laws, and in general new knowledge, which is the engine of the scientific and technologic of humanity. In practice, very few humans have this ability and discipline. But the results of their work benefit all humanity and change the speed of development of our knowledge. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. This allows us to talk about autonomous real-time distributed optimization. The power of artificial intelligence that we can use depends on the support network in the cloud, the local PC that serves as the user interface, and the power of the algorithms that are in the cloud and in the PC. If you want to implement powerful AI, you need to understand informatic, algorithms, and computer programming. The success is directly related to the ability to implement first and second level algorithms. Nowadays, the computer system is very complex and is part of the success. For example, Geoffrey Hinton, the grandfather of artificial intelligence, in a CBS chatbot, indicated that if, in 1986, he had tried to solve the problems that we can solve today, he believed that the computer used in 1986 would not have solved the problem yet. Monolithic mathematical models. With the advent of the digital computer, in 1947, computer-oriented mathematics, and the first digital mathematical models were born. These models, due to the initial limitations of computers, were thought monolithically to be solved in computers with a single processor. This quickly exhausted the dimension of problems that could be solved. Atomized mathematical models. At the beginning of the decade of the 60s of the last century, the researchers presented the first works aimed at dividing the monolithic models, to convert them into modular, atomized, models. In the opinion of the speaker, this effort was made to get models more manageable, which resulted in lower memory requirement, and faster solution of mathematical problems. At that time, there was no parallel computing. To visualize the difference between the information provided by a monolithic model and an atomized model, we can think of a medical examination based on a photograph, and one based on an X-ray. Photography does not allow us to understand what is happening inside the human body, X-ray does. That is an advantage that cannot be achieved with a monolithic vision, which only provides aggregated information. Atomization allows to understand how a system is assembled, and how information flows inside. In 1943, Warren McCulloch and Walter Pitts created the concept of artificial neural networks. They published the paper, A Logical Calculus of the Ideas Immanent in Nervous Activity. McCulloch and Pitts tried to understand how the brain could produce highly complex patterns, by using many basic cells that are connected. They designed their system based on as they believed our brains work, and patterned it after the biological model of how neurons work with each other. The neural networks were growing, and in practice they took the name of artificial intelligence, displacing other methodologies and technologies that also generate artificial intelligence in the machines. Traditional artificial intelligence, based on artificial neural nets, ANN, and support vector machines, SVM, has concentrated its efforts on imitating the mental models of human beings in the recognition of patterns. Modeling efforts, coupled with today's great computational power, have enabled a great development in pattern recognition, definitively surpassing the human capacity for such activity. However, being a mental intelligence older than mathematics and creative, which has grown in the human being based on elements other than science, closer to empirical evidence, these characteristics are transferred to the scientific process of creating an artificial intelligence oriented to mental intelligence. Because of this, its growth has been slow than it would have been, if we had a scientific basis for mental intelligence. Within a nervous system, a neuron is an electrically excitable cell that fires electrical signals called action potentials through a neural network. The neuron is the main component of nervous tissue in all animals. Neurons communicate with other cells through synapses, specialized connections that commonly use minute amounts of chemical neurotransmitters, to pass the electrical signal from the presynaptic neuron to the target cell, across the synaptic gap. Neurons are highly specialized for the processing and transmission of cellular signals. Given their diversity of functions performed in different parts of the nervous system, there is a wide variety in their shape, size, and electrochemical properties. For instance, the soma of a neuron can vary from 4 to 100 micrometers in diameter. An artificial neuron is a mathematical function conceived as a model of biological neurons. Artificial neurons are elementary units in an artificial neural network. The artificial neuron receives one or more inputs, representing excitatory postsynaptic potentials and inhibitory postsynaptic potentials at neural dendrites, and sums them to produce an output, or activation, representing a neuron's action potential which is transmitted along its axon. Usually each input is separately weighted, and the sum is passed through a nonlinear function known as an activation function, or transfer function. The transfer functions usually have a sigmoid shape, but they may also take the form of other nonlinear functions, piecewise linear functions, or step functions. They are also often monotonically increasing, continuous, differentiable, and bounded. An artificial neural net is based on a collection of connected artificial neurons, which loosely model the neurons of a biological brain. Each connection, like the synapses in a biological brain, can transmit a signal to other neurons. An artificial neuron receives signals, then processes them, and can send to neurons connected to it. The signal at a connection is a real number, and the output of each neuron is computed by some nonlinear function of the sum of its inputs. The connections are called edges. Neurons and edges typically have a weight that adjusts as learning proceeds. The weight increases or decreases the strength of the signal at a connection. Neurons may have a threshold such that a signal is sent only if the aggregate signal crosses the threshold. Defining parameters and topology is a combination of empirical work and scientific work, but there is no mathematical theory that must be respected. The algorithmic process is cyclical, and its convergence is based on the minimization of errors. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets, specialized in performing specific pattern recognition. For this, the basic patterns of ANNs are modified. Convolutional artificial neural nets. They correspond to ANN specialized in identifying certain types of patterns, such as images. The image presents an example of an ANN oriented to recognize images of numbers written freehand. The result is a discrete indicator associated to the number read. Generative Pre-trained Transformers, GPT, are a family of neural network models that uses the transformer architecture, and is a key advancement in artificial intelligence, powering generative AI applications such as ChatGPT. GPT models give applications the ability to create human-like text and content, images, music, and more, and answer questions conversationally. Organizations across industries are using GPT models and generative AI for Conda, text digesting, content generation, and search bots. but their ability to solve real decision-making problems, different from advanced pattern recognition, is minimal, if not nil. For many data scientists, data-oriented models are the only artificial intelligence out there. This includes academic teaching. This entails a problem of development of artificial intelligence, since many executives and managers not experts in AI think that the only artificial intelligence that exists is predictive. Then, it is applications such as ChatGPT, and the like, that will be considered the AI of the future. The displaced methodology is formal mathematical modeling using algebraic equations, and/or differential equations. This is related to the use of mathematical programming, or optimization, to support decision-making. It is easy to show that in most companies, mathematical programming is not considered to produce knowledge, like the human. This is because decision-making does not concern researchers who promote artificial intelligence. Practitioners, perhaps fanatics, of traditional AI, have classified mathematical programming algorithms as the exact methods, not with the intention of highlighting them, and promoting their learning. On the contrary, they disqualify them because in theory they cannot be used. But this is false. Thus, with the aim of repeating patterns, several meta-heuristics have been created trying to perform optimization processes, supported by very weak mathematical laws, which simply rely on imitating patterns of behavior of smart beings. But thinking, what to imitate ants, or whales, etc., produces better, or equal, results than optimization based on mathematical laws, is like expecting that these beings had discovered the theory of relativity. Mathematical artificial neural nets. Jesus Velasquez Bermudez creates a special neuron, which he calls mathematical artificial neuron oriented to support the creation of artificial brains, based on the structuring of mathematical artificial neural networks, which follow the mathematical structures derived from the atomization of mathematical systems, and problems, following the methodologies of large-scale modeling, such as those developed by Dantzig and Wolf, Benders, Van Roy and others. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets. The mathematical artificial neuron is a mathematical model, presumably of optimization, which results from the partitioning and decomposition of a monolithic problem into an atomized model, following the mathematical laws of large-scale mathematical modeling. Two mathematical artificial neurons communicate with each other, forming a network of mathematical artificial neurons. Communication occurs in two directions between the two neurons. The communication protocol between the two neurons is defined by mathematical laws developed to solve atomized problems. The modeler can choose the protocol, but not the communication process, which for optimization is based on the scientific laws of duality theory, and for equilibrium problems in mathematical programming with equilibrium constraints, PEC, methodologies. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. A mathematical neuron represents a robot, which can communicate with another robot, autonomously, since it knows the mathematical rules that it must respect. This is what happens in the human brain, where autonomic systems communicate with each other to make decisions. The mathematical artificial neuron is the technological evolution from the biological neuron, typical of mental intelligence, to the neurons necessary to represent mathematical intelligence, which until now are not produced by the human being. Like all mathematics, theory is cadent, and for those of us who already work in high-complexity mathematical modeling, it is the logical step we must take. It's just widening the look, and thinking a little outside the box. The mathematical artificial neuron is a mathematical superstructure, representing a complete system. A mathematical artificial neuron network can be a neuron of a larger mathematical artificial neuron network. This law of transitivity is typical of large-scale modeling. A large-scale system can be represented by a mathematical artificial neuron, and covers multiple subsystems, where each of them can be represented by a mathematical artificial neuron. Using large-scale methodologies, the mathematical artificial neuron can be divided into two, or more, mathematical artificial neurons, forming a mathematical network of artificial neurons. This process can be repeated, until the smallest mathematical artificial neurons, the atoms of the system, are obtained. The greatest advantage of mathematical artificial neurons is that they represent clearly defined objects within a system, that communicate with each other through fully known mathematical laws, and that they comply with laws with transitivity and divisibility laws, in such a way that a system can be atomized, to the level of knowledge that the scientist on duty has. An artificial hypothalamus is a network of mathematical artificial neurons. Each of them represents a system or subsystem. The difference with large-scale methodologies is that the solution is visualized as specialized communications between mathematical problems, while in the artificial hypothalamus the process is cooperative based on autonomy, distributed, and real-time processing. In addition, there is a standardized language for communications between mathematical artificial neurons. Any type of organization can be represented following these principles. The case of a poultry production system is presented. The system has been divided into 6 subsystems, which together make up the poultry production system. Oil and gas artificial brains. From human brains to artificial brains. The creator of the human brain conceived it as the integration of 3 main organs, or systems: neocortex, hypothalamus and hippocampus. The hypothalamus is part of the thalamus. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. The connection between all the subsystems, within and between them, is made by bioneurons. For this, biological neural networks are formed, through which information flows in the brain, and in general in the human body. Neuroscientific studies associate the network of neurons of the cerebral cortex in layers, and in columns, connected in an organized hierarchical way. Although in its beginnings traditional artificial intelligence did not look at neuroscientific studies as a fundamental support, there are currently clear trends of recognized researchers, who consider that neuroscientific studies should be the basis for understanding the functioning of neural networks in the brain. 2 of these researchers are: the neocortex contains millions of neurons that communicate with each other, to capture the world that occurs around the human being. The connectivity of these neurons does not occur based on a dense network, that connects all neurons to each other. Connectivity is based on a sparse network, which can be assimilated to a sparse array. In optimization models, it is common to use a matrix that relates columns with variables, and equations with rows. The normal thing is that these matrices are sparse, structurally similar to that of the human cortex. Everything indicates that the structure, and joint functioning of the neocortex and hypothalamus, is like the structure of the most advanced optimization algorithms. This strong relationship can serve to deepen the knowledge of the 2 disciplines, artificial intelligence and mathematical programming. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. The structures that can be produced can have any topology, like neocortical structures. However, it should be noted that while in neuroscientific studies, topology is not clearly explained, but in the case of large-scale mathematical structures, topology is defined by mathematics, and not by human interpretation. More complex methodologies, such as cross-decomposition, generate cross-structures like the real structures of neocortex. Hippocampus store the experience, and the knowledge acquired over time in the human brain. The learning process of the human being is concretized in memory, which accumulates information to face each new situation using the accumulation of knowledge that has been made up to that moment. This information is stored in the hippocampus where the data is organized according to its age. Like any physical element, Its use affects its reliability, and that is why short memory, the one that stores the data of the last days, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them, remember. The operation of the artificial hippocampus is presented as an expert system that must store two types of knowledge. Formulation, the components of mathematical models, and historical data of the results generated solving the mathematical problems, using large-scale optimization methodologies. This information is used as starting point in future uses of mathematical models to support decision-making. While humans in prehistoric times did not have access to mathematical intelligence, because they were creating it, today it is the engine of human knowledge, and ideally should be handled by all humans. Unfortunately, this is not the case. Therefore, its management must be part of the artificial intelligence that humanity is creating. The same thing happens with creative intelligence, the knowledge created by scientists, and the way to produce it is part of today's human intelligence. Real-time smart and autonomous communication between robots. And it is stored in the artificial hippocampus, an intelligent database on disk, or in RAM, which can be accessed in the next conversation of all robots. Joseph Louis Lagrange was an Italian mathematician and astronomer, later naturalized French. In mathematical optimization, the method of Lagrange multipliers is a strategy for finding the local maxima and minima of a function subject to equality constraints. Using the implicit function theorem, the seminal Lagrange idea is to convert a constrained problem into a form such that the theory of an unconstrained problem can still be applied. Algorithms swarm, the actual state of artificial intelligence using artificial brains. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. The algorithm that simulates the hypothalamus is assembled by Optex, the HI's artificial intelligence to generate mathematical programming solutions, using the models that traditionally make up a decision support system. The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers, will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.